Shri Gurubhyo Namaha, children. Today we are moving on to the last topic of current electricity, which is potentiometer. Now, last class we were discussing about meter bridge, which is a practical experiment for you. Hope you are thorough with the concepts of meter bridge. So, today we are moving on to potentiometer. Now, potentiometer, again, it is a device which is used. Now today we are moving on to current electricity, part 15. The topic is potentiometer. Okay, so this is an instrument which is used to measure an unknown resistance. Okay, unknown EMF, not resistance, EMF, or otherwise you call it as potential difference. Okay, so you can measure the value of potential difference using a potentiometer. Okay, and also this is used to compare the EMF of two cells, and we can also measure the internal resistance of any particular cell whose EMF is psi. That also can be measured using potentiometer. We are going to discuss both the topics now, but before we go on to that, let us see how the potentiometer is. Okay, so it is basically a long piece of uniform wire. Okay, now look at this diagram. Now this is a uniform wire of few meters in length. Okay, now these are the wires, and now this is connected to a cell. You have a cell whose EMF is to be determined. It is connected across this side. Now this wire is cut into several pieces and they are placed side by side. Usually it will be 10 meters wire. Now each segment is made into 1 meter wire and it is connected like this. Okay, and they are all connected by thick metal strips on the side. Now see here, this black color vertical strip is a metal strip through which the wires are interconnected. So this is how the wire goes. Start from A. Now it goes all the way like this. Again, this is a metallic strip which connects this wire and this wire. So again it is connected here. Again it is metallic wire, metallic strip. Again the wires are connected. So the length of this wire maybe it extends up to 10 meter and each segment is 1 meter in length. So this is how the potentiometer wires will be. And here is the other components that are connected: a battery, a rheostat, a variable rheostat, and a key. Now this, by varying this, you can adjust the value of current in the circuit. Okay, and here you have a jockey now which is placed in the, now as we saw in meter bridge, now jockey connects the external circuit with the potentiometer wire, and you move a jockey along the wire at one particular point. The galvanometer shows zero deflection. Now you have a galvanometer that is connected here, children. Now at that point the potential drop, what is the potential drop and what is the balancing length, from that we can find out the value of the potential difference. Okay, so the wire it runs from A to C. Okay, this is what I was talking about, the wire. Now this wire is made up of, now the wire is made up of manganese. Either you will use manganese or you have constantan. Okay, so the wire is made up of this material. Now this material should have a very high resistivity. Okay, so these are the two things you should have in mind when you make the wire of a potentiometer. So it should have a high resistivity and also low temperature coefficient. Okay, so these 2 points are very important for the wire. So the wire should have a very high resistivity and it should have a low temperature coefficient. Okay, and what is the principle of this potentiometer? Okay, now you allow a constant current to pass through this wire. So the current can be varied using a variable resistor. As I told you, when you allow current to pass through this wire, Now this wire is supposed to have a uniform cross-section area, yes or no? So you allow current to pass through a uniform cross-section area. Now you have a potential difference, you have a potential drop. Suppose you keep on moving the jockey from A, keep on moving. Let us consider at this point N1. Okay, when you move the jockey over this wire, the galvanometer will show some deflection. But at one particular point, okay, at one particular point, the let us say that the point is N1 here. At this point, the galvanometer reads zero deflection. Okay, so the potential drop across any length of the wire is directly proportional to the length. See here, now at this point, let us say there is a potential drop here, which means the value, the length is proportional to the potential drop across the cell. Suppose now here this diagram is with respect to comparison of two cells, comparison of EMF of two cells, but imagine this to be a single cell. Now at this point, if the galvanometer is showing null deflection, you measure the length of the wire from A to N2. So this length will give the value of the potential drop, or will give the value of the EMF of the cell. Okay, clear? Okay, children. So if we connect a voltmeter, so to find out the EMF of any cell that is connected, if we want to find out the EMF, you connect the cell across this and you send some current through this wire. Now at a particular point, when the galvanometer shows null deflection, so that length will give the value of EMF of the cell. So the potential drop across the wire will give the value of EMF of the cell. So this can be found out by Ohm's law. So we know that from Ohm's law, what is the formula for Ohm's law? V is equal to I into R, and we know the formula for R as, so R is equal to rho into L by A. Substitute here. So V is equal to I into rho into L by A. So the resistance of a particular material, it depends on the length and the area of cross section. So you substitute the value of resistance here. So rho into L by A, and rho is the resistivity. You all know this. Resistivity depends on the nature of the material. So here, now the current is steady here. Okay, so the current is steady and rho is a constant. Suppose if the material is going to be manganese or constant, the resistivity is going to be constant. And area of cross section also, as I said, you have a uniform cross section area. So the potential drop, so all these things are going to be constant, children. So I constant, rho constant, A constant, and so we can say that the potential drop across this will depend only on the length, which is called as the balancing length of the potentiometer. So where the point, where the jockey shows null deflection, so that becomes the balancing length, and when you measure the balancing length, it is proportional to the potential drop, which is equal to the EMF of a particular cell. So this is the principle of a potentiometer. Okay, ma. Now take your book, page number 122, second paragraph. Now the first paragraph, they explain about how the potentiometer appears to be. Like it is made up of the wires are arranged in such a way that each segment has 1 meter wire, and you have a battery, you have a rheostat, key, everything. So this is about the construction. And the second paragraph you take, children, a current I. So when you allow current I flowing through the wire, which can be varied by a variable resistance. Variable resistance is this one. This is also called as rheostat. Now this can vary the current in a circuit. Okay, so you allow current to flow through the wire. Now the current value can be adjusted through a rheostat. So the wire is uniform, and I said the area of cross section. So it is a uniform wire. So the potential difference between A and at any point L from a distance, Suppose let us say the distance is at this point n1. So the distance, this is the distance from A, it comes here, from here it comes here, then again it goes from left to right, again this is the point where the galvanometer shows null deflection. Okay, so the potential difference between A and any point at a distance L, so this distance is nothing but L, is given as psi of L. Psi is nothing but the EMF. Psi of L is equal to phi into L. Okay, so where phi is the potential drop per unit length. Okay, so this is the diagram. So this is the formula. This is what I was discussing with respect to Ohm's law. I said V proportional to L, here psi proportional to phi of L, which is nothing but the length of the wire from A to the balance point. So this length is measured. So that length corresponds to the potential difference, or which is the EMF of the cell. Okay, so the first diagram here, there are two diagrams here, children. The first diagram shows how a potentiometer is used to compare the EMF of two cells whose EMF is psi1 and psi2. Look at the diagram here. There are two cells that are connected. If we want to compare the EMF of these two cells are connected like this from A, and the points that are marked here. Now this is 1, 2, 3. Okay, now this is a two-way key, children. Now two-way key. Now here let us consider the position of the key where 1 and 3 are. Now either you can connect this 1 and 3 or 2 and 3. If 1 and 3 are going to be connected, this cell is included in the circuit. If 2 and 3 are going to be connected, then this cell is connected in the circuit. So this is how you connect. So this is a two-way key where you can include one cell at a time. So 1 and 3 you connect. So the galvanometer will, now when this is connected, there is a current flow. You adjust the rheostat so that there is a current flow in the circuit. Now the galvanometer will show deflection at a particular point, say at N1. Okay, so for this cell whose EMF is psi1, it is included in the circuit. The galvanometer shows deflection at N1. Okay, now we are going to apply Kirchhoff's loop rule. Now this becomes a loop. Look here, children. Which is the loop? I start from A. Okay, now this is the balancing length, right? So balancing length is measured as AN1. Okay, ma, listen, I look at this arrow. Start from A. Now you keep the jockey on the wire. It goes on like this. Then comes again, goes on like this, comes again, and here at this point the galvanometer shows null deflection. So this is the length, AN1 is the length. And if I am going to consider a closed loop, which is the closed loop? Start from A, then come to N1. From N1 it is connected to galvanometer to 3 to 1, and once again 1 to A. So look at the closed loop. I again repeat, children, listen. A2 through this way up to N1, then from N1 to G, then G to 3, 3 to 1, and 1 to A. So I will write the closed loop to be applying, let me write here, applying Kirchhoff's voltage rule in the closed loop. What is a closed loop? A, N1, G, 3, 1, A. Hope you understood now. Okay, A, N1, G, 3, 1, A. So you apply voltage rule in the closed loop. Then I have the equation to be psi of L1 plus 0 minus psi1 equal to 0. Okay, so next again you include the second cell. Now you have found out the balancing length for the first cell. Now you connect 2 and 3 now. Okay, when you connect 2 and 3, this cell will be included, and again you move the jockey on the potentiometer wire. So the jockey moves, there will be a value of current here, but when comes to at this point, which is called as N2, okay, N2, there will be a null deflection. Okay, so that null deflection, now the closed loop will be AN2, then again G, then 3 2 A. So this is the closed loop for the second cell. So again write that. So we have again applying voltage rule in the closed loop. What is the closed loop now? Again start from, look at the diagram once again children, A to N2. So that we will write A N2. Again it will go to galvanometer, but this time which is the cell that is include? This cell is include. So it is 3 2. You have 3 2 A. Okay, so G 3 2 A. So what will be the equation now? You have phi L2 plus 0 minus psi 2 equal to 0. So when you compare these two equations, I have psi 1 by psi 2 equal to L1 by L2. So as I said you, the potential difference depends on the balancing length. Psi 1 is the potential difference of the first cell, psi 2 potential difference of the second cell, which is directly proportional to the balancing length of the potentiometer wire. So see, psi 1 by psi 2 equal to L1 by L2. So using this mechanism, you can compare the EMF of two cells by determining the balancing length in the potentiometer. So this is one part of the experiment. So this experiment you will be doing. And the second experiment is how to determine the internal resistance of a cell. Now that is the second diagram. You have a cell connected there whose internal resistance has to be determined. Okay, so the same connection, and now here you have two values once again. One is in an open circuit, the other one is a closed circuit. So let us see how it goes. Take page number 122. The paragraph after the equation 3.92, that then after that you have one more paragraph. We can also use, from there this experiment starts children. We can also use a potentiometer to measure internal resistance of a cell. For this, the cell whose EMF is psi and whose internal resistance is R. You know that internal resistance is measured, is represented by a small r. So whose internal resistance has to be measured. It is connected across a resistance box. Now this RB is nothing but a resistance box. Okay, it is connected across a resistance box through a key K2. Now with K2 open, so if the circuit is now in an open circuit, if the K2 is open, now the balancing length is obtained, that is L1 into AN1. In an open circuit, you first measure the balancing length, which is given as let me write here children, psi equal to phi into L1. This is the balancing length in a open circuit, and when you press the key, when you look at this diagram. Now when the key is closed, that is when the circuit is complete, again you move the jockey over this wire, and at a particular point called N2, the galvanometer will show zero deflection. Okay, so that balancing length you write as, now in an open circuit it is EMF, in a closed circuit it is potential difference. So V is equal to phi of L2. Okay, so when you compare this, I have psi by V equal to L1 by L2. Okay, and we know the value of psi to be internal resistance. We have already found out the value. I into small r plus r is psi. And of course, V is equal to I into r. So substitute here. When you substitute, here I have I into r plus r by I into R, which is equal to L1 by L2. So here I gets cancelled. So when I rearrange this equation, I have the value of internal resistance to be equal to R into L1 by L2 minus 1. So this is the formula to find out the internal resistance of a given cell. Is it clear, children? Here I gets cancelled. Now when I rearrange these terms, I will have the formula for internal resistance to be determined by potentiometer. So potentiometer, there are two ways of using it. One is to compare the EMF of the cell, and the second one is to find out the internal resistance of a cell. Okay. Now there is a small problem that is there in your textbook, children, which is in page number 128, example 3.12. Okay. Now in a potentiometer, a cell of EMF 1.25 volt, EMF is psi1. Psi1 is 1.25 volt, gives a balance point at 35 centimeter. So this is your L1, children. So L1 is 35 centimeter. Now if the cell is replaced by another cell, so psi2, I don't know the value of psi2, and the balance point shifts to 63 centimeters. So L2 now becomes 63. What is the EMF of the second cell? It is just a simple substitution. We'll write the formula psi1 by psi2 equal to L2 by L1. Okay, I need to find out the value of psi2. So psi2 is L2 by L1 into psi1. So substitute L2 as 63 and L1 as what is the value of L1? It is 35, children, into what is psi1? Psi1 is 1.25. So when I simplify this, I will get the value of psi2 to be 2.25 volt. So psi2 value is 2.25 volt. Okay, clear? So this is a very simple problem, and you have one more problem, children. Take page number, again the same topic where what we discussed. In that you have an example sum, page number 123. You check in your textbook, children. There is an example problem there. Read out the problem. A resistance of R ohm draws current from a potentiometer. The potentiometer has a total resistance R0 ohm. A voltage V is supplied to the potentiometer. Derive an expression for the voltage across R when the sliding contact is in the middle of the potentiometer. Now look at the diagram carefully, children. Try to understand the diagram very clearly. Now while the slide in the middle of the potentiometer, now if it is going to be exactly in the middle of AC, okay, now actually the resistance is given as the potentiometer resistance is given as R0, children. Suppose let us take the resistance along the wire RC is given as R0. Okay, ma? But where is the null deflection occurring? It is occurring exactly at B. B abindrathu, it is the center, right? So in that case, if the whole wire's resistance is considered to be R0, the resistance at AB will be R0 by 2, correct? And you have one more resistor whose resistance is R, which is exactly parallel to AB. Okay, ma? So you have to find out the total resistance between A and B first. So A and B is inclusive of R0 by 2 and R which are connected in parallel. Hope you understand now. So the total resistance will be 1 by R1 equal to 1 by R plus 1 by R0 by 2. So both the resistors are connected. Actually, this R0 is in the wire. For your clear way of understanding, they are mentioned here. So both the resistors are parallel to each other. So here you have R0, here you have R0 by 2 and here R. Okay, so the remaining part will be, that is BC will be again R0 by 2. But we are calculating the resistance with restricting ourselves to AB. So on the AB you have R0 by 2 and R which are parallel to each other. So you find the effective resistance. I have the value of R1 to be R0 R by R0 plus 2R. Okay, right. Now I am going to find out the total resistance between A and C. So the total resistance will be what? The sum of resistance between A and B and B and C. Now the sum of resistance between A and B, just now I found out. What is that? It is R0 R by R0 plus 2R, plus you have the you have the remaining part which is BC, which is also R0 by 2, right? So the total, the current flowing through the potentiometer will be I is equal to V by R. Now this V by R is, in that R you have R1 plus R0 by 2. So when you simplify this R1 plus R0 by 2, you have 2 in the denominator which is going up. So you have 2V by 2R1 plus R0. Okay. So the voltage V1 taken from the potentiometer will be the product of current and resistance. So V1 is equal to I into R1. So substitute for I as 2V by 2R1 plus R0 into R1. So they are simplifying it. So you substitute again for value of R1. We have found out already the value of R1 as R0 R by R0 plus 2R. Substitute that also here. When you simplify, I will get the value of V1 is equal to 2VR by R0 plus 4R. Is it clear, children? Am I making you the concept clear? So work out this problem, and we'll be continuing with the remaining part of it. Let me see whether I can solve some problems. I want to discuss something with you which I'll be doing it in the next class, children. Okay, ma? See you, children.